Hi, everyone. So this is the transport session. So the policy session is next door if you want to go to that one. I am Ben Wetenhall. I'm a lecturer at Newcastle University and the transport lead for UKCCSRC as well. We've got 3 talks in this session and we'll have time for questions after each talk. Anyway, we'll go straight into it. So first up, we've got Raphael Pfaeltzer from the carbon removers. It should just be good to go.
Is it on the clicker here?
Yeah.
Good. Yes. So, that's great. So, what do we do? Maybe just explaining totally what we do before I go into the projects. So we effectively capture biogenic CO2 only from certain sources, so mainly whiskey distilleries, biomethane plants, basically anything where the CO2 comes out at really high purity to make the capture job really easy. We capture that CO2 and then we effectively do whatever it takes to run a CO2-based company on the back of that CO2. So we aggregate it from multiple small sources. We then sell it as liquid CO2 to the food and beverage industry. We run Scotland's only dry ice factory to make dry ice and then sell the dry ice to the pharmaceutical industry. And we make and we permanently store the CO2 either through geological storage or through a carbonated building material, and then we sell the carbon removal credits that come out of this. But ultimately, we're just a CO2 company and do whatever makes us money on the CO2 that we do. We've been doing this in the UK for a few years now in different ways, and we are currently expanding into Denmark because that's the country where geological sequestration was available for us to buy. In the UK, we weren't allowed to buy sequestration capacity, and that's why we are currently just building a big project in Denmark. When I said why biogenic CO2 and why only biogenic CO2, ultimately the distinction is fossil CO2 is an annoying waste product that is taxed or ETS'd, and you have to effectively pay to get rid of. Whereas biogenic CO2, you can make money on either by monetizing the effect that once you've stored it permanently, you can issue a carbon removal credit on the back of the CO2 molecule, or you can use it as a feedstock. Now we just make feedstocks for dry ice production or for food and beverage companies. But in the future, maybe if these things come to pass, there will be e-fuels, synthetic fuels, power to X, whatever you call these projects, that also needs biogenic CO2 as a feedstock. And then I said we only capture from fermentation sources, so only from biomethane or from whiskey distilleries. In theory, the same tech would apply to wastewater treatment plants and to bioethanol. So there is no large-scale bioethanol really in the UK, apart from one Nippon gases plant. But ultimately, why we focus on this segment boils down to what Jeremy said in the earlier session, thermodynamics rule. And ultimately what we want, what we have to make in order to be able to sell it is we have to make 99.9% pure CO2, track pollutant levels in it, liquid, so minus 20 Celsius plus 17 bar. We have to make that, and if we can start with higher purity sources, we spend less money getting the CO2 to that end state. So if you start from a biomethane upgrader or the fermentation wash tracks in the whiskey distillery or the AD part of a wastewater treatment plant, or for that matter, bioethanol factory, but those aren't really big in the UK, you basically get 95% pure gas phase CO2 out of the CO2 valve. So you have to do very little thermodynamic work to get it from 95% pure gas phase or ambient pressure to 99.9% liquid phase. So very low energy needs, no heat needs at all, very little electricity needs. Therefore, very low cost of capture. The other way of making biogenic CO2 would be if you post-combustion capture of, for example, an energy from waste side or a biomass power station or a biomass district heating station that incinerates wood chips or landfill waste. But in the flue gas of these stations, the CO2 is typically around 12%, and there's a lot of gas separation work required to get it from 12% to 99.9%. And because of the incineration, there's a lot of stuff in there that either the utilization customers or the storage providers absolutely don't want in there. NOx, SOx, oxygen, formaldehyde, leftover amine compounds that are all a nightmare to get out of the CO2 and to get the purity levels that we need to get to. And then obviously, whichever capture and release tech you use, you will need heat to release the CO2 from the capture sorbent. So both the power needs and the heat needs are much, much higher. And then finally, just for completeness sake, because we often get asked about this, so I've included it here. In theory, you could also try and suck the CO2 straight out of the air with a direct air capture plant, but it's the exact same thermodynamic solvent chemistry that the post-combustion systems use. Same stuff, just at, again, much, much lower starting concentration. So you have to do even more thermodynamic work to get it there. So when people say, oh, direct air capture will at some point go to $100 a ton, never possible. Yeah. So we focus on the sources that have the lowest capture cost. However, the one problem these sources bring is they're really small and they're typically in really terrible locations. So the typical source we capture from between 2,000 and max 50,000 tons a year. Most are around 10,000–15,000 tons a year. So you can already tell that, you know, if you talk to the energy from waste people or BECS or the district heating people, their typical sources are hundreds of thousands of tons if you're energy from waste to district heating, a million or millions of tons if you're BECS, power BECS. So they all just have a pipeline put by some pipeline operator to them. The sources we work with don't have that. So in order to make those sources accessible, you have to physically truck the CO2 from the small sources to your aggregation point. And obviously we do this because the difference in capture cost is so massive between post-combustion and fermentation that we can easily afford all this trucking logistics and the liquefaction and still do it cheaper than capturing more locally. So how do we do this practically? That's what it looks like. You know, the blue container, the dark blue container is one of our capture units. The people in the biomethane world call this a capture unit. You come from the post-combustion world, it's mainly a liquefaction unit because it already starts at 95% purity. So there's not much gas separation required. And then we put two of these isotanks next to one of these units, because one unit basically fills one isotank a day. And then we have a third isotank on a truck that basically shows up and picks up one isotank's worth of CO2 every day. And the reason why there's two next to each unit and not one is just that in most sites we can't pick up on some days. So we need to be able to fill two and then have the truck pick up twice on Monday. So practically, what do we currently do? So we already operate this in the UK at a few sites. The upper of the two pictures is a picture from Invergordon Distillery up just north of Inverness from a few months ago. You can see that's one of our capture units there. The commissioning engineer took the noise reduction panels off, so it looks a bit naked there. But usually the noise reduction panels that lie on the floor next to it are around it. Now we actually have two of these units up there. Because it's two units now, there's actually four of these isotanks up there. So we basically capture the and all the pipe work in this big cylindrical thing you see there, that's the pipes that go to the fermentation tanks in the distillery, into which the ambient pressure, highly pure CO2 comes, basically wafting over at very low pressure from the fermentation tanks. We then pick up from partly with trucks with an ISO container or with a big road tanker for CO2, and then we sell it to the food and beverage industry. We feed it into our dry ice factory, and we feed it to someone in the north of England who uses CO2 to treat fly ash from the energy from waste industry to make an artificial aggregate, which is basically calcium carbonate then, so the CO2 is stored in it, and that allowed us to issue a carbon removal credit. So that's what we have been doing in the UK for a while now. Then I talked about Denmark, our next expansion project. The reason why we expanded to Denmark is that we were both able to just buy properly 10-year binding storage capacity in Project Greensand, just off Esbjerg, and we got a part subsidy from the Danish Energy Agency for part of these volumes, to use part of the volumes to make negative emissions for the national emission account of Denmark. And the other part of the volume we use to basically make these voluntary carbon credits that companies buy. We're capturing from 3 to 4 biomethane sites, all strictly fed with waste. Denmark makes a lot of bacon and a lot of cheese, so they have a lot of dairy and pig manure to feed into AD plants. And their credit buyers are very worked up about energy crops, stuff that goes into these AD plants. So the credit buyers like the fact that it's just manure. And then we aggregate from the 3 to 4 AD plants the same way we do in the UK, ISO containers as buffer stores, ISO containers on trucks, some road tankers, and we have to run a gas chromatograph. We run a small station with a gas chromatograph in it. That's what's in the little white container next to the ISO tanks. That's what one of these gas chromatograph stations look like. You basically have to use that to batch release every single ISO tank, because both the utilization customers and the stores only accept stuff that has a batch testing certificate of the pollutant levels with it. So that's what we do in Denmark, starting in probably between April and July 26, with 50,000 tons a year. And then the thing that we've learned in Denmark, which our business doesn't do, but we kept getting so many phone calls about it, that we're thinking that there's probably a natural extension to our business in a few years there. Now, at some point, like I said in the beginning, fermentation CO2 is the lowest hanging fruit in terms of capture cost. But Europe, depending on how you do the maths, Europe only has between 40 and 45 million tons of this fermentation CO2 budget. Actually, has less now. But if the EU meets its biomethane growth targets by 2030 and 2035, then the EU plus Britain as a whole would have around 45 million tons of biogenic fermentation CO2 spewed off the back of all this biomethane growth. But depending on what you think of national emission targets, greenhouse gas removal targets, synthetic fuel blending mandates, 45 million tons isn't enough. So the world will run out of, or Europe will run out of this lowest hanging fruits, and then the next lowest hanging fruits are the post-combustion volumes of BECCS plants or energy from waste. And we've seen this in Denmark, that there's a lot of energy from waste and biomass district heating sites that are around 2, 3, 4, maybe 500,000 tons that just can't convince anyone to build a pipeline to them. If you're 2, 3, 400,000 tons of CO2, the national grid operator just will not build a pipeline to you, because they're busy building the pipelines to the million-ton stations. So we actually got a few phone calls that said, look, we will help you organize the train. We've worked out that our biomass district heating station is like a train a day effectively of ISO tanks. We'll help you organize it, but can you just help us practically do this, rent the tanks, lease the tanks, fill the tanks, batch release the stuff, make it show up on time at the storage handover points, etc. We're a small business, we've never had time to do this, and those capture projects never have a business model because the subsidies aren't high enough to allow for the massive costs of post-combustion capture. But it feels like that this model will probably play some role in that world too in 5 or 6 years' time, once the world has sorted out how to deal with these 45 million tons. Right, let me stop there and hand back to Ben for the next presenter.
No. Any questions, madam? Okay.
Been clashed with donuts.
Sorry, I should have
Chuck down the ears of this question.
Sorry, I should have closed the microphone.
Thank you very much. I'm Raphael Lugman from University of Strathclyde here. I like your business model, which is really nice. And what I'm interested in is the pressure of your CO2. capture? Is it liquefied CO2 or dense phase CO2?
So, I mean, when it comes out the valve at the fermentation side, it's
Yeah.
95% pure and basically ambient pressure. Depends on how the site is designed, anything between 20 millibar and 400 millibar.
Okay.
Once we've processed it through our capture plant,
Yeah.
then it's liquid phase.
Okay.
Standard liquid phase food and beverage grade. So around 17 bar, around minus 20 degrees Celsius.
And it's stored in their tanks.
Yes, yeah, exactly. I mean, the real tank expert that's over there. You can ask him all the tank questions afterwards.
Yeah.
But these tanks are around 17 to 20 bar pressure and around minus 20 Celsius.
About pricing
Yeah. Of what?
of your, you sell to the when you sell your CO2 to the utilization people. About price? How are you priced? How are you making your money?
Yeah, I mean, by selling it for more than we effectively pay the CO2 source for it, plus all our electricity, OPEX, CAPEX financing costs.
Yeah.
So I'm not going to go into too much details, but very round numbers, because you can get these round numbers by just calling up a few farmers that have AD plants. Very round numbers. If a farmer has an AD plant and has already bought liquefaction kit, some have just bought it speculatively, the farmer will tell you that they're not going to go much below 100 pounds per ton.
Okay.
Driving it X works off their lot. We know that some of the big companies, BOC, Nippon, who take really long contracts, like 15, 20 years contracts, they sometimes get it for like between 18 and 90. But I think, actually pick up X works at a site, it's very, very difficult to do it under 100 pounds. And then you just add transport and processing, etc. So if when we get calls from, for example, these synthetic fuels projects, and they ask us to quote them a price, and then we tell them, look, I mean, once we make it show up at your site, and once we distill it to your purity levels, it'll be worth like 200 to 250 pounds a ton. Then they always moan and roll their eyes and hang up on us, because they're not quite used to what CO2 is worth in the real world. Yeah, but that's rough pricing.
Thank you very much.
We are giving volume discounts though, so if you buy a lot, we'll make it cheaper. I think there was another question up there.
Mike Ornsworth from Sheffield University. Do I need it? I'll just show you. I wanted to ask you about the amount of carbon dioxide that you fit in one of the ISO tankers. And then also, if you could say a few words about the safety considerations that you have transporting those on the road.
Yes, so one of these ISO tanks is 20 tons. If you can use a road tankers, the CO2 trucks that look like milk trucks, those are around 32 tons in the UK or 36 tons in Europe. So that's why we sometimes use them, because they're higher. If you try to optimize payload per run, for example, the run goes over a toll bridge or something, but otherwise these. And safety considerations, I mean, yes, there are. So this is all the drivers, whether you use this way or the tankers, you have to have ADR trained drivers. This is just the standard ADR shipment in a way. So there are safety considerations, but it's not explosive. It's an asphyxiant. But so we have to do the dispersion modeling every time we put this stuff on there. But to be honest, it's pretty standard, because Nippon Gases and BOC and LED have been doing this in the utilization industry for a long time.
Thank you.
Hi, Harsham from Desnes here. So it looks really cool, and it's really nice seeing your kind of plans for expansion. Do you see much of a market in terms of a demand for that CO2 looking up to 200 million, or rather to your expansion to things like capturing from post-combustion?
Yeah, I mean, I'll go back to the very first slide, because ultimately, or to the second slide, ultimately the current utilization market, no one really knows how big it is in the UK. Every time we raise funds, our investors ask us for a market study, and there is none. about how much utilization CO2 is used. Everyone's best guess seems to be that it's around 1 million tons in the UK, probably a bit less. So, that gives you an idea of what the UK does. And other countries in Europe are similar, just scaled up or down by GDP effectively. So the only way this ever grows to 45 or 200 or any number that's much bigger than 1 million for the UK is if either of these things grows. So either people pay for negative emission, greenhouse gas removals, whatever you call it, or people pay for synthetic fuels based on non-fossil CO2 feedstocks. And those two things will only happen if there are compliance schemes that force people doing either of these things. We sell these voluntary carbon removal credits, but at a scale of thousands, or maybe if it's going really well, tens of thousands per transaction cumulatively over the contract period. So, the voluntary market isn't going to get to millions in either of these things.
Yeah.
So we have to be patient until the compliance stuff kicks in.
Thank you. And sorry, one other question on the kind of midstream side of things. Do you see any issues with essentially there not being enough supply of things like ISO tanks? If there's lots of companies like yours or lots of people looking at non-pipeline transport and going to ISO tanks for CO2 transport?
I'm laughing because I also sit on the non-pipeline transport working group with some of your business colleagues, and there's a lot of industry people there who keep brainstorming about this problem that there wouldn't be enough capacity and that they need business help to underwrite it, subsidize it, take the asset risk and all this stuff. And I can be honest, look, what we've seen in Denmark is once some of these contracts were publicized, once we said we've signed storage contracts, once Vincent said we've signed 350,000 tons worth of storage contracts, within 2 weeks we had 3 local SMEs that just are road hauliers calling us up to the contact form of our website, said like, look, we are road hauliers. You need CO2 haul. I'll buy the isotanks. I'll buy the road tankers. Like, if you give me a contract, I think there's enough entrepreneurial spirit out there, especially in the haulage industry, that as soon as people are out there, there will be contracts. I think if people know the isotank industry better than I, at the volumes we need to buy isotanks, they're easily available. And to be honest, they're not that difficult to make. Once someone wants 15,000 things, I'm sure manufacturing capacity will scale up. I think the Danish approach was basically the government just said, make this happen, gave people contracts to make it happen, and the value chain has sorted itself out at a small scale, which worked very well there.
Thank you.
Thank you. Very cool. Thank
you.
Yes, yeah. Good afternoon, everybody. So I'm Sergey from University College London, and well, this is the talk about the work that we have done from using the desktop studies around the so about the desktop studies that we did at UCL in the number of projects, and particularly the project called, you cannot still see the slide, yeah. Sorry, and particularly the project that was called C4U and recently called by 2030. So these are funded by European Commission, and about the CO2 transport in industrial clusters, and the scope of this presentation first. So I will give some very brief background on the CO2 transport, most of which probably you are quite familiar with, but then I will move to the challenges and barriers to implementation of CO2 transport as a solution, a vital solution for carbon capture and sequestration and storage, and then those solutions that we proposed in terms of the to aid the implementation of CO2 transport in the project in one of the clusters, and this will be followed by some summary and future recommendations. So there is definitely the demand for CCS, and well, the graph here shows the projected amounts of CO2 that needs to be captured, utilized, and stored according to IEA GHG agency, and we can see that by 2050, there's about 1 gigaton of CO2 that needs to be captured globally. And well, given that the amount of CO2 that is in demand for utilization is tiny compared to this amount, well, definitely we need storage. And well, given the mismatch between the places where CO2 is emitted and where it should be stored, of course, we need to have the transport solution. So this is what we know quite well. The good, and obviously this is the challenge. Well, we need to have that transport, those transport solutions. So the good news is that, of course, well, CO2 transport is considered as a mature technology, and we have several modes of CO2 transportation. So these include pipelines or other mobile modes of transport using road transport, railway transport, ships and barges, and they all come with some advantages and disadvantages. Some of them I have listed here based on the literature, and well, particularly pipelines are considered as most suitable economic mode of transport of CO2 over long distances and large amounts, but they come at a high upfront capital costs. And well, for small amounts, and they're depending on the availability of the infrastructure in terms of the roads, for example, or waterways, we can go for other modalities of transport. They offer more flexibility, less of an upfront cost for implementation when it comes to implementation, but still operating and operating costs can be quite high, and we can compare the different modes depending on specific needs. Well, amounts that needs to be transported and distances that CO2 needs to be transported, and here basically comes the challenge: how to decide on the exact specific mode of transport, especially if we are talking about several emitters and several options where CO2 may need to be transported either for storage or for utilization. How these transport modes capacities can be estimated, or there is the economic side of and well, cost benefit analysis that needs to be done. Efficiency of the operation is another challenge, and there are, of course, safety risks that also need to be considered, given the safety issues with CO2 itself as the asphyxiant, and also some impurities that can be detrimental to CO2 transport facilities, may cause corrosion issues, or they can be hazardous on their own. So apart from these design and operation challenges, technical challenges, there are also other non-economic challenges which are posed by the environmental impacts, for example, of CO2 transport when it comes, for example, to using mobile modes of transport that operate on fossil fuels. There are issues with the potentially with the policies and regulations when it comes to obtaining permits for transport, cross-border transport issues, resolving financial liabilities, long investment cycle for CCS projects, and uncertainties of the ownership of CO2 transport infrastructure. There can be differences in the stakeholders' agenda when it comes to, for example, implementation of CCS in the cluster regions, where the emitters would like to join at different times. They may wish to pull at different times as well from the projects. They may have their own decarbonization agenda when they implement other measures to reduce their carbon emissions. And of course, the aspect of public perception. This also can be detrimental to the project if there is a strong opposition to CO2 transport infrastructure implementation. One of the solutions that we will, you're probably, you're now, of course, well aware of, is the reducing the cost by clustering CO2 emitters. And this brings the benefits of reducing the cost, reducing the initial investments, reducing the risks to the project implementation. There are a number of such projects proposed in the UK. There is a project that we're working on in terms of the research infrastructure, in terms of the transport infrastructure research at the border of Netherlands and Belgium in the North Seaport, and in such clusters, well, CO2 transport facilities need to be decided and planned in terms of rollout over a number of years, and even well, it can be applied to clusters. It can be applied to larger regions. Well, there are several optimization problems that have been studied to address this infrastructure design. And typically, well, people looked in the past at the design of CO2 transport networks, pipeline networks, to connect several emitters and to transport CO2, for example, to geological storage. Well, these studies were done around Europe and other regions around the world. There are also studies where the cost optimal modes of transport are investigated, for example, for CO2 transport chains, when you collect CO2 from a source, a number of sources, and transport it to dedicated storage using pipelines, trucks, railway ships, and barges. And there are also studies where, apart from cost criteria, other criteria were included in the multi-criteria decision analysis to figure out what network configuration or transport infrastructure solution to go for. So these can be safety considerations, for example, or environmental impact. So people have studied that as well. And there is a huge demand currently in such tools where the infrastructure planning is done for considering multiple modes, but also multiple criteria. And this is where we came in the project. And well, my talk will be, the rest of the talk will be basically about this. But in the project, we have several partners, and well, some of the partners are listed here, and they also looked at the business models for CCS and also applying systemic analysis on policies and societal readiness in CCS, including CO2 transport. And this is in the context of implementation of CCS in industrial clusters. So on the side of infrastructure planning for an infrastructure design for industrial clusters, what we have done is that we have constructed a methodology where cost analysis was balanced by the environmental impacts, and we performed this for the case studies for the scenarios of CO2 transport in a cluster, predefined scenarios. Well, the test bed for our studies was the North Seaport cluster, as I have mentioned here. There are 5 emitters here, 5 major emitters. Overall emissions from the cluster are around 20 megaton per year. And well, the ambition is to capture at least 45% by 2030. So this is the scenarios that we have looked at, and some configurations for the transport solutions that we have analyzed using this multi-criteria analysis are shown here. So we compared 2 alternatives where we have either pipeline transport, agglomeration of CO2 from emitters in the region and transported to the dedicated point from where it can be transported further down for geological storage, or using barges, again, agglomerating to the same point from where it can be transported elsewhere. So the boundary was of the battery limits were around the cluster itself. And what our results have shown is that, well, for a number of scenarios here, the bar charts show 8 scenarios of pipeline transport as shown here, and will be transport by barges. And you can see here that, well, the pipeline transport is most economic, but if you compare the environmental impacts, for example, the global warming potential, then they're really quite comparable, and the pipeline transport environmental impact is slightly bigger. In all the cases, well, the bottom green and the purple parts of the bar chart show the contribution of pipeline and liquefaction and compression, so operational costs associated with the two technologies. They are contributing quite a lot to the overall costs. And we have performed also the multi-criteria Pareto optimization here to figure out what are the most optimal scenarios for CO2 transport network design in the cluster region. Once we have done that, we have also looked at the economics of CO2 transport in the cluster, where apart from the cost, we consider the penalties that companies may need to pay over a number of years when construction takes place. And this particularly applies to implementing CO2 pipeline transport solutions. So here, the bar charts, well, they show the costs associated with the CO2 pipeline project implementation, either in year 0, where it is just all CapEx and OpEx, or in the number of years afterwards, where the company will pay, well, the companies will start paying emission penalties according to ETS price. And you can see that this just goes up with the years, and after a certain number of years, it may happen that using shipping as a mode of transport will become more economically attractive. So after like 2 years, well, we can see that will be overall cost of CO2 pipeline transport project will be more than what you will have if you go for shipping option. This finding indicates that the ETS price as the main incentivizing instrument for CCS is one of the key factors determining the economically preferred choice of the mode of CO2 transport in CCS clusters in Europe. Well, we have looked at the 2030 scenario of decarbonization of the cluster, and came up with the pipeline network solution, for example, as shown here, connecting the 5 emitters in the region. So that network configuration was optimized given the geographical constraints in the region. And our partner at the University of Sheffield have developed a nice tool that enables predicting the expansion of such a network in the future for the 2050 scenario, when more emitters are supposed to join the cluster. And they have done that by explicitly taking into account for the times when these emitters are planning to join. So there were assumptions made, well, in consultation with partially with industries when this may happen, and they have predicted what will this be the evolved network configuration. So this is they have developed really nice tool, which is close to commercial implementation really. So in a summary, well, I just would repeat that, well, choosing the optimal CO2 transport solutions requires balancing costs against other criteria, and this could include, well, geographical constraints, safety, societal acceptance, environmental impacts, and the speed of deployment. And in our project, we have developed tools and methods that enable us to predict the infrastructure for CO2 transport, including, well, right sizing of such a network, planning the future expansion of CO2 transport networks, and also we have the opportunity to do the multi-criteria optimization of such networks, including, well, not only cost, but other criteria such as, well, for example, environmental impacts. Well, we have produced a list of publications that you can access through these presentation slides, and we have the several publications and deliverables made available through the project website, and we partially continue this work in several other projects, well, Calby project and in-case project, and there we look also at the optimal monitoring of optimizing monitoring systems for CO2 transport networks, and also evolving CO2 transport infrastructure for producing green methanol in Pfaeltzer project. Thank you very much for your attention. I'm happy to take questions from you.
Introduce four scenarios to pipelines, one, two for shipping. Targeting 1.2 million ton carbon dioxide transport per year.
Yes, yeah, there were.
What about the difference among them or the cost? I couldn't understand it. What's the difference if you have one of the scenario, but what about the cost?
Yes, I guess, well, you're referring to this slide, is that right?
This one.
Yes, yeah. Yes, here we for example,
We haven't mentioned it, just only have targeting 1.2 anti CO2 per year for scenario A. Is it the same for all of them?
Yeah, well, we have made the assumption that we are capturing exactly the same amount of CO2 from the emitters in the cluster. So that's
cost analysis for all of them.
Yeah, yes, yeah, we have done the cost analysis for all of them.
Can you describe which ones can be implemented?
Yes, yeah, well, in terms of the cost analysis, for example, here we have the results for 8 scenarios, and we have pipeline scenarios as shown here for the 35 bar transport and for the 110 bar pipeline transport, with the offtake at 2 different alternative points, so that's why there are 2 here. And we've had shipping scenarios, so this included, well, milk route and also hub and spoke when you are transporting individually from the emitters to the dedicated collection point. And well, in terms of the cost, well, we have the budgets for the cost in the top here. So there are like CapEx and OpEx, and well, we have the well, in fact, in this plot there not really split as a CapEx and OpEx. So in full paper, well, this was presented in the conference last year. Well, you have finally for CapEx and you can find results for CapEx and OpEx, but here they are just enumerated costs, and but you can see cost of liquefaction and compression contributing quite a lot, but the cost for pipeline as the CapEx here, well, it is the CapEx cost here. They're relatively small, and the cost of shipping, so that's the tonnage cost. Given the small distances, well, this cost is comparatively high to the pipeline cost in the project in that area. So it's small distance, it's like 30 kilometers span. So that's fine.
We have any other questions?
Just to follow up on this question, thank you for the presentation. when you say the pipeline, is it a new pipeline or an old pipeline which is already in the sea?
Yeah, we have assumed that these are new build pipelines.
Do you
But
show
the important point is
it's new build everything for the environmental? It's everything new built.
yeah, that's right.
And do you include port infrastructure as well? Just the ship?
It's the liquefaction and compression infrastructure, which is also included. So interim storage, for example, that you would require to provide all the same conditions for the offtake of CO2 from the intra-cluster region, really. So it's we assume that from the cluster itself, CO2 then will be transported in dense phase at 110 bar pressure. So the conditioning will be needed if you switch from conditions for shipping, which is saturation conditions around 20 bar up to 110 bar.
Another question, Mike?
Yes, Steve Matthew from Store CO2. Could you show the slide that shows the graph of pipeline versus shipping, where you take it down to like 2 million tons?
Pipeline versus shipping. Oh, it was.
That one.
Yes, yeah, right, yeah.
So if I'm is that showing, according to your analysis, that if I can't read it that well, does it say is the
Yeah,
bottom
the
2 million
distance-
tons per annum? Is it going 2,468 million tons per annum?
Yeah, that's right, yes,
Yeah. So that is that indicating that for 2 million tons per annum, a distance of, is that 400 kilometers?
Yeah.
The pipeline transport would be cheaper than shipping. Is that correct? Is that what that's saying?
Well, that's what it is saying based on that specific study. Really. So it's pick this up as an illustration of the fact that there were optimization done to decide on the optimal mode of transport. I know that this may maybe very case specific. I'm not familiar with the details of the background study for
Right.
this specific paper that was done some years ago. By since.
But I represent a shipping company, and
Right.
that's ultimately some of our own analysis where we built our business model on a slightly different interpretation. It'd be interesting to see what that graph is as you go further down, less than 400 kilometers. Essentially, if you're looking at the UKCS onshore to offshore, you're 200 kilometers is about as maximum as you're going to go. And we still have a business case for shipping.
Right.
You know, even if you just take into consideration the oil and gas industry, you know, why do so many smaller fields that weren't part of the original connection points for the Fortis pipeline or the Sun and Mo pipelines, they use floating vessels with ship export rather than new build pipelines. So it's, you know, just something I think consideration that it does, to me, the message seems to be unduly kind of penalising a shipping approach.
Yeah, right. Okay. I think, I take your point. Yes, yeah. I should have more carefully looked at the studies to illustrate this optimization studies behind to convey the more precise message. But there were more studies since then. I think that was 2014, quite early study, and probably very case specific, I would say.
No, so yeah, it's certainly very interesting work. So thanks for sharing it. I just make that.
Thank you for the question.
Okay, thank you, Sergey.
Yep. Hello, everyone. Good afternoon. My name is Joseph Rainey. I'm here to give you a sort of very high level overview of the various products. Chart Industries stroke Howden offer to the CCUS market. I very much appreciate I'm the last speaker of today, and I think I've got 10 minutes to wrap up here. And I'm also standing in the way of a nice refreshment for you all, so I'll try to keep this as brief as possible. So for those of you not familiar with who Howden are a Scottish company that are headquartered here in Glasgow since 1854. James Howden, the founder, he's done a lot of early work. He developed the forced draft system, which made boilers more efficient, which allowed steamships to cross the Atlantic. Since then, we've grown considerably, and so did our range of various products, which was mainly rotating equipment. So that's fans, compressors, heat exchangers. Now, Howden is a Scottish company, was a Scottish company. Very recently, we were acquired by a large American company called Chart Industries, and that happened in 2023. Both companies were about 6,000 strong employees. So we've came together, and we like to use the word synergies. So both companies were sort of selling into each other and offered sort of various complementary products to each other. So now we have 115 global locations, 12,000 employees. It's a vast array of products, and I am still learning them all. Sometimes I go to events like this and somebody educates me on stuff we actually make. But we have various products, including the CCUS markets. And we're just going to talk you through some of them. So we have here, this is just a sort of slide which is showing you 4 of the main brands, because when we usually acquire companies, or and in this case, Chart acquires us, we like to keep the branding because it has a lot of recognition. So in the CCUS market, the 4 main brands which we have are Raphael Labs, which is sort of smaller scale, started in breweries, but I'm going to talk about that later. We have SES, Sustainable Energy Solutions, which is a carbon capture technology. We have the legacy Howden, which is, all the rotating equipment and mostly used in the transportation if we're going through pipelines. And we have legacy Chart, which is like tanks and stuff, but we'll cover those in more details. So that last slide showed us, various products at various sizes, from small scale up to very large scale. This graph here is showing us like, no matter where in the process it is, there is products that we have to go into, whether that's, usage, storage, transport, or the actual separation processing, or the actual capture itself. So if we do a wee bit of a deeper dive into the legacy Howden products, we'll see here at point source capture, there is large centrifugal fans, axial fans, rotary heaters, blowers. For direct air capture, we have fans and the rotary absorption machine. I'll come on to that in a second. And then during the separation process, we have the compressors, various types of compressors and blowers. And then when we get to transport and storage, again, larger compressors, larger pressures with big recips and screws and diaphragms. The RAM here is interesting in the direct air capture, because all these other products are used in various industries and various gases, but the RAM was specifically made for carbon capture. It is based on one of our other technologies. You'll see the gas heater at the point source capture. It's the same graphic, but that is, it's an absorption, swing absorption, where you have like the gas stream going up, and it rotates round, goes into an absorber, and then is released on the other side of the heater. And I can't say too much about it, unfortunately, because we're covered by NDA, but it is something which we see a sort of major growth for. We've been working on it since 2011. And we had some hurdles at the start because the initial absorbents weren't effective enough, but now we have a very large partner who's very invested in it. And we have had a sort of working prototype since 2023. So that's something which we are quite excited about. Again, continuing with the rotating equipment, it's just a sort of slide to show the sort of breadth of products we have and the various flows and pressures that they go up to. Basically, I don't want to sound too sales, turn this into a sales speech, but just basically know that if there is a need for any rotating equipment, it's always something that we're going to have a solution for eventually. And please ignore, sorry, number 7 and 9. I did ask marketing to take them out of this graph, but they've not. There are some blowers which have been divested quite recently, so they've not updated this sheet. Okay, and another piece of rotating equipment here, which plays a very important part, is a rotary gas heater. So we've seen these before in the FGD plants, where it basically takes untreated gas, cools it down, allows it to go through the treatment process, and then reheats it as it goes up the stack. So we are seeing these applications and inquiries for carbon capture plants. You'll see there on the picture down at the bottom, that is what it would look like without this. If you're using some, a wet stack, and you see a sort of very visible plume, and then in the picture in the middle is actually Drax with one of these heaters installed, where you cannot see the sort of the treated gas coming out the high stack. And why we find this important, because we have a demonstration plant in Japan which is actually using this technology on carbon capture. You'll see there it is they're encircled in the middle is a small sort of demonstration plant here. It has a booster fan there in the B position. So any gas or leakage which comes through is actually treated gas, which then gets pulled in and sent through the process again. So we're not putting anything nasty up there. And if I move on, this is just to show that we also do the fans and the blowers for those applications, because we've done them in FGD. It's just to show they are quite arduous depending on where they are in that process, but we always have a solution, and so they are there with live references in the field. And talking about references, here are some just actual carbon capture projects which we have supplied products into. And not only actual live projects, we're always involved in various feeds, pre-feeds. And for about the last 15 years, we're just continuing to support all the various projects which we see. So that is basically the sort of Howden rotating equipment products. I'll now very quickly throw you through some of the chart ones. Again, so this is a chart company, ACS, which is actually captures the CO2 rather than just a product which is supplied into a certain plant. It's not amine solution, which I suppose most of you here are familiar with. It actually cools and compresses the CO2 into a solid, separates it then, and then reheats it into liquid format. And then with, as we were talking about earlier, all the tanks. So Chart is very big into cryotechnology, and it's a very large tank manufacturer. So they do multiple sizes of vertical, horizontal tanks to suit any size and demand. And they have like a metal outer jacket, so they've not got any sort of foam insulation in there. They do without that. Into some transport pieces, they also have the ISO containers. They have on trailers, and they also looking at and can do the railroad trailers as well. Now, I'm just coming to the end, but since you're all going for a drink, just wanted to touch on Earthly Labs, which was a product which was started off in the States, and it takes CO2 from breweries, and it captures that CO2 again, as we were talking about. It's a high concentration point of CO2. It takes that and it treats it. It then compresses it, it dries it, it treats it some more, turns it into liquid CO2, and then that brewery can reuse that CO2 later on in the process. So we talk about the environment, how it's great for the environment, and these breweries love to sort of promote that, but the real reason they do it is money, because you've got an ROI of probably typically about 2 to 3 years for a situation like that, depending on the volumes you're going through. And that's just a sort of graphical representation of what you would see in a sort of a large brewery with that system installed. And again, as we touched on earlier, we see a large market for this. We are upscaling that at quite a rate, and we're looking at all the various biomethane plants, biogas plants in Europe, upgrading to biomethane and then taking that high purity CO2 and then liquefying it and monetizing it. And that is me. If you have any questions.
In the last slide, what the minimum temperature you go achieving CO2?
Pardon?
What the temperature, what the minimum temperature? Here. What the temperature you go in that low temperature?
I'm not sure. It depends on the pressure they're at as well, but I'm not sure of the exact temperature, but probably be around about minus 15 to minus 20, depending on the pressure they're hitting. Yes, it's just, yes, and there you'll see the tank there. That's a liquid tank. Yes.
How many tons per hour, day, year, whatever you express it, does one of the Strathclyde systems?
Can we do?
Yeah.
So it's sort of, it's because it's modular, we're going up. So we have just quoted 50 tons per hour. Well, on the small end, it is 9 tons per year.
Question?
Yep.
If you consider applying this all your technologies to certain to processing certain amounts of CO2,
A system.
well, compression, for example.
Okay.
If you use several units for just go for a big unit.
Yes.
There are significant economies of scale there because of the less material use or.
Yes, certainly. Yes. So very typically, Howden has always been about the larger projects. So yeah, all our compressors are sort of all for the bigger scale. We don't really sort of at the smaller end. There's so many other suppliers that we're not as competitive, but in the bigger end, that's where we sort of come into our own, and definitely that's where the sort of economies of scale come in. All depends on the customer if how much redundancy they want. But yeah, the less machines you have, the far more economical it's going to be.
Last question?
Okay, thank you.